Okay, so good afternoon. We left off. We had if I recall correctly, a relatively brief but rich discussion about rational functions, right? That culminated in the formal definition of vertical and horizontal asymptotes, right? And so what we did is we said, here's what we're going to do to get past this notion that an asymptote is an imaginary line that the graph gets closer and closer to. We're going to give it a formal definition. Vertical asymptote is as x approaches a number, the graph goes to infinity or negative infinity, and then a horizontal asymptote is that as x goes to infinity or negative infinity, the graph levels out, gets closer and closer to a number, right? Remember that? And then I gave you an assignment that turned out to have really nothing to do with what you had talked about, but it kept you busy for a couple seconds anyway, so mission accomplished, all right? Okay, did we do the long run and short run behavior here of this one? I don't think we did. So let's use this as a little refresher, okay? So let's do the long run behavior first, which is also known as the end behavior. So the long run behavior is what's happening a long ways away at negative infinity and at positive infinity. So if we start with infinity, as x approaches infinity, what happens to the graph? No, sir, disagree. We had this discussion last week. We've already gone through this, and I thought I'd kind of talked your way out of it, but no, good question. But we are starting from the middle and going to infinity, so we're not trying to approach infinity from one side or the other. We're just going towards it. What is it? But we need to be more specific. What value does it get closer and closer to? 0, right. So as x approaches infinity, y approaches 0. And then as x approaches negative infinity, so if we go the other way, what does y do as we go to the left? Yeah, also, whoops, not equals, y also approaches 0, okay? So that's called the long run behavior because that's what's happening a long ways away from the middle of the graph. The short run behavior is what's happening in the middle, okay? And so to figure this out, we have to figure out what is the value that x is approaching that is like meaningful in this case. What x value is important in this graph? 0, okay, yeah, because there's something funky going on at 0. So this is where we're going to do the positive or negative thing. So I'm going to do the positive first. As x approaches 0 from the positive side, so that means when we start on the right-hand side of 0 and then follow the graph, what does the graph do? Goes to infinity. So as x approaches 0 from the positive side, y goes to infinity. And as x approaches 0 from the negative side, y also approaches infinity. So in this case, both of these are the same. So what that means is this information right here tells us what? This tells us that we have a horizontal asymptote. Well, why didn't you say it? Yep, at y equals 0. Okay? That's why. And then what does this tell us?
Vertical asymptote.
Okay, this says that we have a vertical asymptote at what? X equals 0. Okay, and then what we're going to do in this chapter is, or this section, we're going to figure out how we can tell where those asymptotes are without looking at the graph, and also there's some funky things that happen with them. From this day forward, I grant all of you the right and the privilege to, instead of writing horizontal asymptote, just write HA, and instead of writing vertical asymptote, just write, yeah, VA. Okay, I'm going to write the whole thing out. Yeah, maybe not. I don't know. I don't know. I'll try and be good, okay? All right, so first thing that we're going to do then is we're going to take these asymptotes and use them to shift the graph around. So this says sketch a graph of the reciprocal function shifted 2 units to the left and up 3 units. So what does the reciprocal function normally look like before anybody starts shifting it? Okay, that's the equation for the thingy is y equals 1 over x. Okay, good. I get a branch of this in quadrant 1, and I get a branch of this in quadrant 3. So this is my original graph, y equals 1 over x. Then if I have to shift it 2 to the left, all that's going to do is it's going to take this vertical asymptote at x equals 0 and move it adonde to the left 2, and then the horizontal asymptote that was at y equals 0 is now going to be at y equals what? It's going to be at y equals 3, okay? And so nice job me by not giving enough room. And then now you can just draw the graph basically the same way. Like Nate said, it's going to be in the first and third quadrant, so just pretend these are your new axes and draw your graph in the first and third quadrant, and there you got it, okay? That's 1 over x squared. Okay, so is that what you're trying to get to me with this thing? Okay, that's 1 over x squared, very close. It doesn't ask this, but I feel like it's something that'll come up later. What's the equation for this? If I move it 2 to the left, I have to go, you were asking me about this when we were doing the marble slide on Friday, x plus 2 underneath the fraction, and then if I want to move it up 3, then I need a plus 3. Yeah, good, on the outside of the fraction. Okay? Pretty much ready for calculus. Yeah, let's get rid of this pre-stuff and just get after it, right? Okay, same thing there. We don't need to do that, right? You got it? Okay. Okay, so the definition then of a rational function, I tried to get you sort of thinking a little bit this way on Thursday when we introduced this for the very first time. Remember, a rational number is any number that can be represented as a whole number divided by another whole number. A rational function is the same thing, except for instead of being one number over another number, it's one polynomial over another polynomial. Okay? Please don't make fun of my speech impairment. Okay? Sometimes when I get nervous, you know, comes out. All right? So that's why I said when we started talking about this that things are getting a little bit crazy here because this thing can be any type of polynomial that you want, and so can that. Okay? All right, so let's start out with a word problem here. Well, we did a word problem Thursday. We started out the rational functions with the distance equals rate times time. Let's try another guy right here. So this is a large mixing tank. I wonder what we're mixing. Currently contains 100 gallons of water into which 5 pounds of sugar have been mixed. We're going to open up a tap, and it's going to pour 10 gallons of water per minute into the tank at the same time as someone pours sugar into the tank at a rate of 1 pound per minute. What we want to do is we want to find the concentration of sugar in the tank after t minutes. So how do you find the concentration of something? It is a ratio, yeah. Awesome. Concentration. Okay, so the concentration of sugar will be a ratio of the amount of sugar in the tank divided by the amount of water in the tank. Okay? Yeah, very nice. So what we need to do is we need to come up with 2 separate equations, one for the sugar, one for the water, and then we need to divide those 2 bad boys, and that will be the formula for our concentration. All right? So they're both real simple. What is the formula for the sugar? No overs in just the sugar. We're just how much sugar is in there at any time t. It's starting with 5 pounds, so I'm going to go 5 plus how many pounds are being added per minute? 1. So I'm just going to go t, just to tick you off. What's the formula for the water? 100 gallons of water to start with. Maybe we're making like taffy or something, I don't know. Plus 10. Okay, now Nate wants to use a different variable, but I disagree because these are both being added at the same rate at the same time. So, I mean, different rates, but over the same time. So it's 100 plus 10t. Okay? So then to figure out the concentration, I just take the sugar divided by the water, and then I'm good to go. Okay? Yeah, that's exactly why we need the same variable. Yeah. Eli, you got your book open to this example page? Okay. Do they do anything else with this? Nobody's looking in their books. Okay. I'm just like, that's it? No, we need Brianna. I don't know. Brianna's not here. She's our truth keeper, which means it's time for the word of the day. What was it last time? No, too easy. Okay.
Yes.
No. Grassroots. Okay, yeah, no, I know. Okay, so if Cassidy or Brianna, is anybody else gone today, comes in and says grassroots, then they get credit because that means they actually watched the video. But if they don't, well, if they don't, then everybody else does, okay? Okay, so I think it was Sophie who asked the excellent question last week. Are we going to use the things that we learned in the other sections in this section? Because it seems like at the outset what we're doing now is totally unrelated, right? Okay, well, here is that moment, all right? So what we're going to do now that we have a good understanding of what a rational function is we're going to try to use the algebra that we've learned previously to find the asymptotes and the intercepts, okay? And so to start with, we're going to do the vertical asymptotes. And this is worth writing down if you're a note taker, with one exception. I don't know what that is. Hopefully they'll tell us. A vertical asymptote will occur whenever the denominator is undefined.
What does that mean exactly? Like, what is the undefined?
I want to go for 0. So what we're going to do is we're going to take the denominator of the function and we're going to set it equal to 0. And then the answers that we get, that's where the vertical asymptotes will be. Okay? So, for example, I'm going to make you mad by going back here when you're trying to write this down. Here we had a vertical asymptote at 0 because that's when the denominator equaled 0. And then over here we have a vertical asymptote at x equals -2 because x equals -2 is when the denominator of that would equal 0. So that's how we find our vertical asymptotes. So, Sophie, what we're going to do is we're going to take the things and we're going to set them equal to 0, and then we're going to have to use like factoring and synthetic division and the quadratic formula and stuff like that to figure out when they're equal to 0. Hey, play a nerd in real life though. So my wife and I have had that conversation a lot, not like that I'm a nerd, but when you watch a lot of different movies and you see them sort of play the same kind of roles, it makes you think that might be kind of how they are, right? So if you're like watching a lot of movies and, oh, it's that guy again, he's always like a jerk, and you're like, he's probably a, you know. That's why Jennifer Aniston, you just know she's such a sweetheart. Every movie, except for the new one, the talk show one. Yeah. Oh, yeah, right. Well, you know. But she's a mom. She's a mom in that at least. Yeah. Oh, really? Same name every time? That's awesome. All right. So this one says find the vertical asymptotes of the function blah, 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 blah. So what we need to do is we need to take and set the denominator equal to 0. So Sophie, here we are using what we learned earlier in the chapter because I have a myriad of ways of solving this problem. Okay, I'm going to try and take the easy way out. There's one thing that I don't like about it, and that's the fact that it's written backwards and that this is a negative. So I'm going to start by switching everything around. I'm going to make this positive x squared, positive x, minus 2, and technically negative 0, but that's exactly the same, so nobody cares. Okay? Now how can I solve this? I could factor, I could quadratic formula, I could complete the square if I was insane. No, he's not going to complete the square. I'm going to go with what I think is the easiest one, which is just factoring it. Two numbers that multiply to be negative 2 and add to be 1 are. How about positive 2 and negative 1? Okay. Yeah, I know. Oh, I just had the meanest thing on the tip of my tongue. No, because I like Trace too much. It was a good one, though. It was such a good one. Okay, so that means x equals negative 2 and 1. Okay, so if we graph this, then we would have vertical asymptotes at x equals negative 2 and 1. Do you trust me? Do we need to go to the back cave and graph it, or are you good? Back cave? Okay.
I need sound effects.
Back cave. What was the function? I don't know.
5 plus 2x squared.
Is on top. 5 plus 2x squared. Okay.
2 minus x minus x squared.
What is it?
2 minus x
X squared plus x.
minus x squared.
Okay, and you were promised vertical asymptotes at 1 and at negative 2, and vertical asymptotes at 1 and at negative 2 is what you shall get. Okay? Okay? Yeah. So, math works. What do you know? All right, what else we got? Let's try another one. So we're just practicing our different ways of, oh, you guys are going to like this one a lot. You're going to love this one a lot. Okay? All right, so same thing. Vertical asymptotes occur where the denominator is equal to 0. Oh, and I'm so glad that we went to the back cave. So I'm going to take this and set it equal to 0. Okay? This is important. Something funky is about to happen. I'm going to factor this into plus or minus 2. So that means that x is equal to negative 2 or 2, right? Yeah. So your assumption would be that since those are the places where the denominator equals 0, that we would have a vertical asymptote at negative 2 and 2, right? Okay, let's go back to the bat cave and let's see what happens here. Okay, let's go back to the bat cave and see what happens here because something funky shows up. Oh, it's just x, thank you. That would have killed the whole thing. But then this is x squared minus 4, right? Yes. All right, so I promised you a vertical asymptote at negative 2 and 2. This time, however, I was unable to deliver because there's only a vertical asymptote at negative 2, but there's not one at 2. Can any, yes? Nope, that's not it. Okay, let me write this out in factored form. There you go. Yes, okay. Don't call that guy a dumb jock. He knows what's up. Because the x minus 2 on the bottom cancels with the x minus 2 on the top, we do not get a vertical asymptote at that place. We still do get something funky that's going on there. If I very carefully run to 2, you get a hole in the graph at x equals 2, okay? Because you know that it's undefined right there because you can't divide by 0, okay? But the only thing that is different is that since it cancels from the top, you don't get a vertical asymptote. What we get there is called a hole, but what we will officially call it is a removable discontinuity. And the reason it's called a removable discontinuity is because you can just remove it by canceling these things, okay? And if I regraph this in its canceled form, in other words, this and this cancels, gives me 1 on top, that gives me just an x plus 2 on the bottom, you will notice that these two graphs are exactly the same with the exception of that one missing hole there is now filled in on this graph here, okay? So there's the one with the discontinuity here at x equals 2. And then if I shut that one down and turn the other one on, then that discontinuity has now been removed, okay? Because we canceled it. So there's nothing on the bottom now that's making it 0. And yeah, it's because the top and the bottom were the same, okay? Okay, thought you had that one there, Cooper, but not quite. Yeah, oh well. We good? Is that? Okay. Okay, so this is the summary of what we just did. I don't know if you want to write that down or not. Okay, so go ahead and take a minute to write that down. The vertical asymptotes of a rational function occur where the denominator of the function is equal to 0, but a hole occurs in the graph if the same number makes them both be 0, okay? Okay, horizontal asymptotes are a horse of a different color, okay? So here's what I'm going to do for you. I learned this vocabulary just last year when I was teaching calculus, and I really like it a lot. We are talking about rational functions, right? So there's a polynomial on top and there's a polynomial on the bottom in each case. Yes? Okay. What we can have is 3 different cases. And they use all this fancy language that I've used before to explain the different things. The first case is when the highest exponent on the bottom is bigger than the highest exponent on the top. What I learned last year that I really like is to call this one bottom heavy. Okay? So bottom heavy means the highest exponent on the bottom is bigger. Okay? So if you have a bottom heavy rational function, then what you will have is, let me rewrite this in a different way. So bottom heavy means a horizontal asymptote at y equals 0. Okay? And so this to me is easier than this whole funky thing there. Notice that all we have to pay attention to is the highest exponent, not the sum of the exponents, not anything else except for the highest exponent on top and the highest exponent on the bottom. What do you think is another case? Top heavy, there you go. So another one that you could have is where the highest exponent on top is larger than the highest exponent on the bottom. In that case, we're going to refer to this as top heavy. And when you are top heavy, that means no horizontal asymptotes. Okay? So when the highest exponent on top is larger than the highest exponent on the bottom, then there won't be any horizontal asymptotes. As x approaches infinity or negative infinity, the graph will either go up forever or go down forever. Okay? Yeah. And then what's the third case? Equal, middle heavy. They're the same. Okay? Yeah. Are you good here? Okay. So. Okay, we're good. Okay. Okay, did you get this one? You could, Sydney, always just watch the recording later.
I'd rather not.
Okay. Okay, this is a little bit hard to explain, but it's easy to demonstrate. If you have the highest exponent on top and bottom equal, then you can cancel those. So just like they've done here, the highest power on top is x squared, and the highest one on the bottom is also an x squared. So those x squareds would cancel, and then I would have a horizontal asymptote at y equals 3. Okay, because when the variables are gone, that's what's left. So I just write that as a over b. That doesn't really make a lot of sense, but hopefully it'll work. Can we close the windows now? I think the hot spell is over. Thanks, though. All right, so let's take a look. Okay, for our sugar example. Are we top heavy, bottom heavy, or equal? Equal. Yeah. We're the same, okay? And so what I would do with this is if I have t plus 5 divided by 10t plus 100, I'm only concerned with the terms that have the highest exponent, so all I care about is the t over 10t. The t's cancel, so that means I have a horizontal asymptote at y equals 1/10 or 0.1, which means in this case that if we keep putting in more and more and more and more and more water and sugar at the same rate, the concentration of sugar in the tank will get closer and closer and closer to 0.1 or 10%. Okay? What? Well, it's 1 over 10. So this t canceled and left me 1. Okay, and these don't matter. Okay, all right. Okay. Okay, what about this one now? So let me save you some trouble. To figure this out, remember that we're only concerned with the highest exponent term. So I don't have to FOIL the whole x minus 2 times x plus 3 thing out. What's my highest term going to be on top? X squared. What is my highest term on the bottom going to be? X cubed. Okay, so that means that this is a case of what? Bottom heavy. So no horizontal asymptote. No, there is one.
No, it's at y.
It's y equals 0, yeah. So bottom heavy means there'll be a vertical asymptote at y, horizontal asymptote. Good Lord. You are wrong, Sophie. So since this is bottom heavy, we'll have a horizontal asymptote at y equals 0. They also asked us to figure out the vertical asymptotes. Where will my vertical asymptotes be? 1, -2, and 5. Do any of those cancel? No, this one's close, x plus 2, x minus 2, but they're not the same, so they don't cancel. Okay? Shall we go to the back cave?
Yeah.
Okay. That wasn't as good. So x minus 2 times x plus 3. X minus 2 times x plus 3. That's on top. And then what was on the bottom? X. No, he won't. He hardly understands. Did you say x minus 5? Okay, thanks. All right, so I told you, I warned you, rational functions are a little bit on the crazy side. Here's a great example. We have a horizontal asymptote at y equals 0. This one, strangely, crosses through y equals 0. So then it's going to come up and get after it from the bottom. And then this one gets to y equals 0 from the top. And then I have a vertical asymptote at x equals negative 2, x equals 1, and x equals 5 as promised. Okay? 1, negative 2, and 5. Horizontal asymptote, y equals 0. Okay? All right, let's save intercepts for tomorrow. Okay?
Maybe that's because